See, this is the last application of thermodynamics first law. So, and through this demonstration or through this discussion, we will develop some new thermodynamic function, which I will introduce after two or three more lecture. But we can see that here from this thermodynamics first law, we can evaluate, or we can develop the idea for that thermodynamic function. See, this is a process given. One process A is given, which is a isothermal process from this state to this, from this state. This is initial state to this final state. Another process B is given, that is reversible adiabatic. Reversible adiabatic, and expansion is basically we are considering here. And another process here I am taking C, that is isochoric process from this point to this point. And similarly, in the subsequent process here we have taken this isotherm, same isotherm A is this, but this time uh, we are not moving from A to this point, T1 point, via a reversible adiabatic followed by isochoric. Rather than we are moving isobaric followed by isochoric. So from initial state, this is initial state, this is final state, and this is initial state, this is final state. So both, in both the cases, the initial and final states are same, but we are following a different path to move from initial state to final state. So change in internal energy, delta U. So usually we write this with E. So I am writing this E not U, delta E, right? So delta E, delta H, Q and W, and this is the new thermodynamic function Q by T, Q reversible by T, right? So let's do one by one. First, I am taking A, 1 mole gas, 1 mole gas, P1, V1 and T1, right? P1, V1, T1. Here, see P1, this is V1 and temperature T1. And this, this is moving reversibly and isothermally. Isothermal, right? 1 mole gas, and P2, V2, T1, right? So this is this A, path A. So as we are very much clear that if temperature is constant, then delta EA is equal to 0, right? And delta H A is equal to 0. We are very much clear about this. Whatsoever the process, reversible, irreversible, any kind of process, if temperature is constant, then change in internal energy and change in enthalpy along that path, that is 0. Now WA, Now WA is equal to minus RT1, temperature is constant, that is T1, RT1, ln V2 by V1, right? And QA is equal to minus of WA as per the thermodynamics first law when delta E is equal to 0. So this is equal to RT1 ln V2 by V1, V2 by V1, right? And delta Q by T. So basically this is QA by T. This is equal to R ln T and T cancel. Because temperature is constant, so there basically T1 is their temperature. So T cancel. So R ln V2 by V1. V2 by V1. So we have determined all the parameters along this path A, right? Internal change, enthalpy change, work, heat, and heat by temperature, right? Now come to the B. B is basically 1 mole gas, 1 mole gas, P1, V1, T1, right? P1, V1, T1, and it is moving reversible adiabatic. Adiabatic. 1 mole gas and P3, V3, P3, V3, and T2. See, see, this is not V3, basically this is V2 because next we are moving isophoric. Okay, so P1, V1, T1 and P3, yes, P3, V2, pressure is different. Okay, see, now it is clear. So V2. So this is adiabatic process. So Q is equal to QB is equal to 0. QB is equal to 0. And delta EB is equal to CV T2 minus T1. And delta HB is equal to CP T2 minus T1. Right? QB is equal to 0. Okay. Now, first law we can apply. So, WB is equal to delta EB is equal to WB. So, this is equal to CV T2 minus T1. So, we have calculated work as well. And what about delta QB by T? This is equal to 0. This is equal to 0. So with respect to B, path B, adiabat, we have calculated this. Right. Now come to the next path C, that is isochoric. Path C, one mole gas, one mole gas, P3, V2, T2, and reversible isochoric, reversible constant volume, one mole gas, and P2, V2, T1, right? P2, V2, T1. See, this is isochoric V2 and P2, okay, P2 and T1, yes, right? So this is the path C. Now, see, constant volume. So WC is equal to 0. WC is equal to 0. So delta E is equal to delta EC is equal to delta QC, and this is equal to CV T2 minus T1. Sorry, T1 minus T2. This minus this. T1 minus T2, right? Similarly, delta HC is equal to delta HC is equal to delta QC, and this time this is equal to CP T1 minus T2, right? Okay, and QC, that is equal to this. QC is equal to CV T1 minus T2. T1 minus T2, right? So delta QC by T is equal to what we can write? Delta Q by QC by T is equal to, we can write here, CV ln T1 by T2. T1 by T2, right? So this is delta Q C by T. This we can write. Clear? Clear to everybody? So this delta Q by T we can evaluate by using this equation. Very simple equation. Now see, A, if we compare A versus B plus C, because B plus C will bring the same final state as A brings the final state. Delta EA is equal to 0. Delta HA is equal to 0. QA is equal to RT1 ln V2 by V1, V2 by V1. WA is equal to minus RT1 ln V2 by V1, ln V2 by V1, and delta QA by T is equal to R ln V2 by V1, right? Now see, delta EB plus delta EC, this is equal to what? 0, and this is equal to delta EA. I mean, we can write this or not. See, here CV T1 minus T2, and here CV T2 minus T1. So if you add these two, this is equal to 0, and basically uh, this is equal to the change in what internal energy along the path A, that is also 0. Now same case with delta H. Delta HB plus delta HC is equal to 0 is equal to delta HA. Now QB plus QC is equal to CV T1 minus T2, but this is not equal to QA. Similarly, WB plus WC is equal to CV T2 minus T1, but this is not equal to the WA. But this C delta Q by QB by T plus delta QC by T, this is equal to R ln V2 by V1, right? And this is equal to delta QA by T. So what conclusion we can draw from this observation? That this Q by T along this path and Q by T along this path plus this path. Q by T is same. Q is different. Q is different, but Q by T is what? Same. So this is our next thermodynamic function. I am preparing you people for that basically. So this we can say that this delta Q by T basically this results. So we can put a note here. This result suggests that this delta Q by T reversible, right? Is a state function. State function, right? Means Q reversible by T, it is a state function. See, we can prove here. Now I am taking another path D, right? Now see, if you take D. So what is D here? See in the figure, D, constant pressure from here to here and then E, right? So first I am taking D, delta ED is equal to CV. So first we can summarize the state basically. 1 mole gas P1 V P1 V1 T1 and reversible constant pressure. So 1 mole gas, 1 mole gas P1 and what, V2? Yes, V2 and T3. P1, V2, T3, right? P1, V2, T3. Now see, T1, T2 temperature is not constant, so delta ED is equal to CV T3 minus T1. This minus this. T3 minus T1. Delta HD is equal to CP T3 minus T1. Right? And QD is equal to delta H basically, because you know what is delta H? Delta H is the net heat change at constant pressure. So here pressure is constant. So this is equal to Cp T3 minus T1, right? And WD is equal to minus uh, V2 minus V1, or we can write here P2, what, constant pressure P1 minus P1 V2 minus V1, because this is a constant pressure. So at this point you can write P delta V is equal to R delta T. So you can write minus R T3 minus T1. Right? So WD is equal to this, you can write. So what is this? QD by T. So QD by T is equal to CP ln T3 by T1. T3 by T1. Right? So this time QD is equal to this. Okay? Clear to everybody? Okay, good. Now come to this process, E, this process. So T3 P1 V2. So this time E, path E. 1 mole gas P1 V2 T3. Reversible constant volume. So 1 mole gas and V2, and this time pressure is what, P2? Yes, P2. P2 and T1. P2, T1, right? So this time delta E is equal to CV T1 minus T3. T1 minus T3. Delta H E is equal to CP T1 minus T3, right? And this is the isochoric moment. So WE is equal to 0. So QE is equal to CV T1 minus T3. T1 minus T3, right? So delta Q E by T is equal to CVLN T T1 by T3. T1 by T3. T1 by T3, right? So all the parameters I have written. Now compare A versus D plus E. A versus D plus E. D plus E. See, delta EA is equal to 0. Delta H A is equal to 0. QA is equal to RT1 ln V2 by V1, V2 by V1. WA is equal to minus RT1 ln V2 by V1, and delta QA by T is equal to R ln V2 by V1. So this is A. Now delta ED plus delta EE is equal to see CV T1 minus T3 and CV T3 minus T1. So this is equal to 0 and this is equal to delta EA. Similarly, delta HD plus delta HE is equal to 0 is equal to delta HA, right? Now QD plus QE is equal to R T3 minus T1, R T3 minus T1, and this is not equal to QA. See, QE CV T1 minus T3 and QD CP T3 minus T1. So CP T3 minus T1 and CV T1 minus T3. So if you add subtract this, so you will CP minus CV is equal to R. So you can prove this. See how QD. D, what is QD? CP T3 minus T1. CP T3 minus CP T1 plus what is QE? CV T1 minus T3. CV T1 minus CV T3. This is equal to CP T3 and CV T3. We can write CP T3 minus CV T3 and plus CP T1 minus CV T1 CVT1 minus CPT1. CVT1 minus CPT1. So here T3 we can take common. So Cp minus Cv is equal to us. Here we can write RT3 and plus CVT1 minus CPT1, right? So RT3, here we can take minus T1, we can take common. So minus T1, so Cp minus Cv, so this is RT1. So we can write here RT3 minus T1, right? So Qt plus Qe is equal to RT3 minus T1, which is not equal to Qa, right? Similarly, WD plus WE is equal to what? Minus RT3 minus T1. WD plus WE. WE is equal to 0 and WD is equal to minus RT3 minus T1. So WD plus WE is equal to minus RT3 minus T1, right? And this is not equal to the WA. Clear? Okay. Now QD, delta QD by T, right? Plus delta QE by T. This is equal to R ln V2 by V1, and this is equal to delta QA by T, right? Now see QD by T. QD by T, what we have calculated? QD by T. QD by T. CP ln T3 by T1. CP ln T3 by T1 plus QE by T. What we have calculated? CV ln T1 by T3. CV ln T1 by T3. T1 by T3, right? So this we can prove this is equal to R ln V2 by V1. See, so see this we can write this is equal to Cp ln T3 by T1 minus Cv ln T3 by T1. So this is equal to Cp ln T3 by T1 and minus Cv. In place of Cv we can write Cv ln T3 by T1. In place of Cp we can write R plus Cv. R plus Cv, right? R plus Cv. So here we can write R ln T3 by T1 plus CV ln T3 by T1 minus CV ln T3 by T1, right? So this term is cancelled, and this you can write R ln V2 by V1, right? So this is equal to R ln V2 by V1. See how this V2 by V1 we can write. If you see here in the step D, what you can write? P1 V1 P1 V1 by T1 is equal to P1 V2 by T3. P1 V1 by T1 is equal to P2 V2 by T2. General formula. So since it is a constant pressure condition, so this is cancelled. So what you can write? T3 by T1 is equal to V2 by V1, right? So this you can write here. So this you can prove here. Now see, QD plus QD, this is QD and this is QE. So QD by T and QE by T is equal to this, and this you can write this. So R ln V2 by V1, and this is equal to this QA, R ln V2 by V1. So we can say here that this delta Q reversible by T, it is what? State function. And you know, now I am disclosing that function, but I am not going right now to discuss that function. That this function is basically called entropy. This is entropy. From here, we develop the definition of entropy, right? Q reversible by T, right? So this is a state function, and finally, this is called entropy. Entropy, state function. Right? So this Q by T, ratio of Q by T along in path, this is a state function. So this is, always equal whether you are moving constant pressure, adiabatic, isothermal, isochoric. If states are same, then this entropy change is also what? Same. So, but this, second law of thermodynamics, in which we develop the definition of entropy and other properties of entropy, I will discuss after thermochemistry. So now I will start thermochemistry, right? Thermochemistry. Thermochemistry. So, okay. So, see, in thermochemistry, basically, our focus is to determine the heat change in energy for chemical reaction. So now our focus is for chemical reaction, how to calculate the change in energy, basically heat energy, we are going to measure here. So how this heat energy change or change in heat energy can be measured for a chemical reaction. So this time a little bit difference is there with respect to the previous cases what we have taken before this. All are physical processes in which gas is expanding or compressing, heating or cooling, like that phenomena is taking place. Now we will focus the heat change or change in energy uh, for chemical reaction, right? So for chemical processes, right? And not only for chemical processes or for chemical reactions, not only for chemical processes or chemical reaction, but along with this, here we will, I mean, focus those processes as well in which there is no direct cleavage of bond, but any kind of intermolecular dissociation is taking place. So, chemical processes or reactions and processes 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 involving involving the cleavage of intermolecular forces, intermolecular forces, intermolecular forces. So, like formation of solution, when any solute is dissolved in a given solvent, then also there is some energy change. So, but in that case, it is not necessary that every time chemical bond is, I mean, going to be cleaved. Some physical forces may, dissociation of physical forces may take place. So, in thermochemistry, our main focus is for chemical processes, chemical reactions, and processes involving this uh, cleavage of intermolecular forces, and what is energy change in that processes. Energy change. So for energy change, to explain the energy change in processes, we have two thermodynamic functions, delta E and delta H. See, this delta E tells about the heat change at constant volume for physical processes. But here we took the heat change at constant volume and constant temperature. And remember always that this is not equal to 0 for above said processes. This is equal to 0 for this is equal to 0 for expansion compression process, but not for such type of processes. And delta H is defined at delta Q at constant P and T, and this is not equal to 0 for such processes, right? So this is called, net heat change at constant temperature and constant volume is called change in interenergy for chemical processes or processes involving the cleavage of intermolecular forces. And net heat change at constant pressure and temperature is called delta H are enthalpy change for this chemical reactions and processes involving the cleavage of intermolecular forces, right? So see, this is constant volume function and this is constant pressure function. Now the point is that which function is preferred here in thermochemistry. So very clear here that delta H is preferred function, preferred function. The question is why? Why delta H is preferred? The reason is constant volume, I mean measurement and monitoring, it is difficult. So under constant volume condition, the measurement of heat change and monitoring of reaction is difficult and it involves the risk. So that's why we prefer this. See, I am not telling that we cannot determine delta E for any chemical reaction. There is no constraint in the determination, experimental determination. But the constraint is that the monitoring of reaction and study of any chemical reaction is difficult under constant volume condition, right? And there is always a risk involved in the constant volume systems. So that's why this delta H is preferred. And you know, this delta E is determined in bomb calorimeter. Bomb calorimeter. And this delta H is determined in open bomb calorimeter. Calorimeter. Here pressure is constant and here volume is constant. So this is bomb calorimeter in which volume is constant and here pressure is constant. So now it is clear that we always prefer this delta H because constant pressure systems designing, monitoring, and every aspect of this measurement of this heat change at constant pressure is what easy for us. That's why we prefer delta H. Clear to everybody? Okay, good. Now see, delta H, if for any reaction, delta H is positive. If it is positive, so in such case, the energy is absorbed by the system because you know the same sign convention what you have discussed, what we have discussed in the previous lectures, you have to use the same. Delta H positive means Q positive. Q positive means heat absorbed by the system, and here what is the system? System is the container having some chemical reaction, so heat absorbed by the system. So such type of reactions are said to be endothermic reactions, right? So such type of reactions are endothermic. Endothermic. And if delta H is negative, delta H negative, if it is with the negative sign, so the heat released, and when you have written this heat released by the system, then don't put the sign with magnitude, right? So heat released by the system. Heat released by the system, right? So the reaction is said to be, reaction is, such reactions are exothermic. Exothermic. One very important question is, arises here, that since if temperature is constant in both the cases, and delta H is not equal to 0, so what is the source of energy here in chemical reaction? Because we know that all of you are knowing that the temperature is basically important factor to change the energy, although work is also there, but temperature, that will controls the flow of heat energy from system to surrounding, like that. And here we are taking temperature constant. So at constant temperature, what is the source of energy for chemical reactions or in such type of processes? So it is very clear that at constant temperature, the source of energy is basically the chemical bonds. So basically, we try to find out how much energy is changing during chemical reactions. And what is chemical reaction? Chemical reactions are defined as the process in which old bonds are broken and new bonds are formed. So in a chemical reaction, due to this association and dissociation, due to this process, energy is changing. And you know, energy changes with temperature as well. So if we change the temperature in this system, then the energy will change with the bond and as well as with the temperature. So we cannot exactly figure out how much energy is changing with respect to the bond energy, bond dissociation and association. So basically, what this delta H is measured here at constant T and constant P, that will directly indicates the strength of bonds, or that will directly measure the bond strength, the strength of chemical bonds present between different atoms. So delta H for any chemical reaction is the measure of the energy change with respect to the chemical bonds. Energy change with respect to the chemical bonds. So we can here clearly mention that the source or the main source of energy change in chemical reactions at constant temperature. At constant temperature is the bond association and dissociation. So the main cause of energy change in chemical reactions at constant temperature, at constant temperature is the association, dissociation, association and dissociation of chemical bonds and or intermolecular interactions. Intermolecular interactions, right? Why I have not written here sole cause? Because I have not covered different aspects like phase change, like resonance, When a molecule, a product is formed and have some resonance, so in the resonance also some energy is changing. So that I have not here covered. That's why I have written here main cause, not the sole cause, right? But this is very broad word, intermolecular interactions. So this is very broad word, and in this I have covered almost all things like hydration, hydrogen bonding, dipole dipole interactions, ion dipole, everything I have covered here, intermolecular interactions, right? So the main cause is this. Some other factors may also be there to change the energy, but that is also related with the some this molecular interactions, right? So the main cause of this association and dissociation of bonds, chemical bonds, or intermolecular interactions. And all of you should, must be knowing that in association, energy releases. In association, energy, whether association of chemical bond or chemical bond formation or intermolecular interaction, energy released. And in dissociation, always energy absorbed. Energy absorbed. And if you measure this energy at constant temperature and constant pressure, then this is delta H. So delta H is negative here, and here delta H is positive. So in every dissociation process, whether it is intermolecular dissociation or this is dissociation of chemical bond, always energy is required. In every kind of association, whether it is chemical bond or intermolecular interactions, energy is released, means delta H is negative, right? So this is the main cause of energy change in a chemical reaction. Hopefully all of you are getting this point. So now it is clear that we are going to use delta H, a thermodynamic function, to assess the energy change in chemical reactions. So in this unit of thermodynamics, we will discuss different types of chemical reactions and how to calculate and how to evaluate energy change, keeping in mind that whatsoever we have defined initially, that delta H is extensive and it is a state function. Every property what we have defined for this function, that is applicable here also. The only difference is that here in chemical reactions, we take this heat change at constant T and constant P. But in the physical processes where expansion and compression is only taking place, in that situation, we will take at constant pressure only, not at constant temperature, because in that case, if you take constant temperature, then delta H is 0, right? So this is the overview of delta H. In the next lecture, I will discuss this delta H and standard enthalpy, how it is defined, what is the meaning of standard enthalpy change, right, like that.